planar graphs and graph coloring. Concepts. Concepts means definitions. Definition. Concepts and definition. Planar graphs first. Definition. A graph is said to be planar or embedded. A graph is said to be 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 planar or embedded in a plane. Planar or embedded embedded in a plane. In a plane. If and only if it can be drawn, if and only if it can be drawn, if and only if it can be drawn in a plane without crossovers. In a plane without crossovers. Without crossovers. Without crossovers. Without crossovers. Such an embedding is called a planar such that such that such that an embedding means fixing. Nothing but it is a fixing. An embedding is called is called embedding is called embedding is called planar embedding. Planar embedding. Planar embedding. Planar embedding of the graph of the graph of the graph. Otherwise is called non-planar. OW means otherwise. It is called non-planar graph. Non-planar. Non-planar graphs. Non-planar graph. Examples. V1, V2, V3, V4, V5, V6, V7. This is a planar graph. Planar graph. Planar graph. V1, V2, V3, V4, V5, V6. This is non-planar. Consider V2 is non-planar graph. Non-planar graph. Non-planar graph. Non-planar graphs. Okay. Some properties of planar graph. Some properties of planar. Properties of planar graph. Planar graph. Properties of planar. First one. Sum of the degrees of the regions. Sum of the degrees of regions. Degrees of regions. Sum of the degrees of regions. Sum of the degree is equal to the twice the number of edges. Equal to the twice the number of edges. Number of edges. Symbolically, sigma d r I equal to sigma E of G. That means sum of degrees of regions equal to twice the number of edges. Yes. Second. Number of regions are less than or equal to 2 by 3 number of edges. Number of regions are of regions. Number of regions are less than or equal to 2 by 3 of the number of edges. Number of edges. Number of edges. Number of edges are number of edges are less than or equal to thrice the number of vertices. Less than or equal to thrice the thrice the thrice the number of thrice the number of vertices. Kn is planar if and only if n is less than 5. Kn is planar if and only if and only if n less than 5. N less than 5. Theorem. Theorem 10 marks, most important. Theorem. Page number 193. Page number 193. Theorem. Statement. If G is a connected planar graph, if G is a connected, if G is a connected planar graph, graph G is a connected planar graph. G is a connected planar graph with n vertices, e edges, with n vertices, e edges, and regions and R regions. Spelling mistake. There is a mistake and R small R regions. All R regions. R regions of a connected planar graph of a connected planar graph. Connected planar graph. Connected planar graph. Connected. Then n minus e plus r equal to 2. R equal to 2. Here these are regions. This is done. Then proof. Proof. We prove this theorem by induction. We prove this theorem by mathematical induction or induction on the number of regions of R, the number of regions R, number of regions of the given graph G, the given graph given graph G, given graph G. If R equal to 1, R equal to 1, then there are no cycles in G. Then there are no cycles in G. No cycles in G. No cycles in G. Then G is a tree. So by the known result, then G is a tree. Then G is a tree. G is a tree. It follows that edge is a cut edge. So by known result. Known result. So by known result, we have E equal to n minus 1 equal to n minus 1. And hence n minus E equal to 1. And hence n minus E equal to 1. N minus equal to 1. Then n minus E plus R. Then n minus E plus R that equal to 1 plus 1 that equal to 2. Therefore, result is true for R equal to 1. So, result is true for R equal to 1. R equal to 1. R equal to 1. Now suppose that result is true for a graph G with k regions. Let the result is true for graph G. Result is true for graph G. Graph G. True for graph G. With k regions. K regions. K regions. Means by induction hypothesis. This is nothing but by induction induction hypothesis. Induction hypothesis. Let G be a connected plane graph. Let G be a let G be a let G be a connected plane graph. Connected plane graph connected plane graph with k plus 1 with k plus 1 regions, k plus 1 regions. Delete one edge. Delete one edge. Delete one edge. That is common to the boundary of two separate regions. That is common. That is common to the boundary of two regions. To the boundary of two separate regions. Separate regions. Separate regions. Separate regions. Okay. Then the resulting graph G1 has same number of vertices. The resulting graph resulting graph resulting graph G1 has the same number of vertices. Has same number of vertices. Same number of vertices. Same number of vertices. One fear edge and one fear region, because the deletion of edge makes two regions in one graph. Thus E1, N1 and R1. If E1, N1 and R1 are respectively the number of edges, vertices and regions the number of the number of the number of edges, vertices, and regions for G1. The number of edges, vertices, vertices, and regions for G1. For G1. Then E1 equal to E1 equal to E minus 1, E1 equal to E minus 1, N1 equal to N1 equal to N, R1 equal to R minus 1. Therefore, N minus E plus R, N minus E plus R equal to N1 minus E minus 1, E minus 1 plus R minus 1, R minus 1, R minus 1, N1 minus E1 plus 1, E minus 1 that equal to plus 1 minus 1 get cancelled. That equal to N1 minus E1 minus E1 plus R1 that equal to 2. So therefore, N minus E plus R equal to 2 by induction. Result follows that by PMI, principle of mathematical induction. Hence result follows. Hence result follows. Hence result follows. Hence result follows. One more theorem. Corollary. If G is a simple planar graph, corollary means a sub-theorem. If G is a simple planar graph, G is a simple planar graph. Simple planar graph. A simple planar graph. If n is greater than or equal to 3, n is greater than or equal to 3, then E is less than or equal to less than 3n minus 6. 3n minus 6. Oh. Let G be a simple planar graph. Let G be a simple, simple, planar graph, planar graph, simple planar graph. If n is greater than or equal to n is greater than or equal to 3 without loss of generality. WLG means without loss of generality. Without loss of generality. We can suppose that G is connected. We can suppose that we can suppose that G is connected. G is connected. G is connected. But otherwise, consider each component G. Since G is a simple, since G is a since G is a simple means simple graph meaning simple. G is a simple. So D of Ri greater than or equal to 3. Greater than or equal to 3. For all Ri belongs to capital Ri belongs to R. Ri belongs to R. That implies sigma Ri belongs to R of G. R of G. Dri. 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 Greater than or equal to 3RG. 3RG. Equation number 1. But R equal to 2EG. Sigma R belongs to R of G. Ri belongs to Ri belongs to R of G. R of G. D of Ri equal to 2E of G. E of G. Hence 2E of G. 2E of G is greater than or equal to 3R of G. 3R of G. 3R of G. 3R of G. Then by Euler's formula. Then by Euler's formula. Then by Euler's formula. Then by Euler's formula. N of G. N of G. N of G. Minus E of G. E of G. Plus 2 by 3. E of G. 2 by 3 E of G is greater than or equal to 2. or E of G, E of G is less than or equal to 3n of G, 3n of G minus 6. That implies E less than or equal to 3n minus 6, 3n minus 6, hence proved, hence proved. Example, this is also important for 10 marks. Example. Show that a planar connected graph, show that planar connected graph with each region of degree greater than or equal to 5, and each vertex of each vertex of each vertex of degree less than or equal to 3 must have at least 30 edges, must have at least 30 edges, 30 edges. So solution, solution, solution. Given that 5 regions, given 5 regions, 5 regions less than or equal to 2 edges modulus 2 edges and 3 vertices, 3 vertices less than or equal to 2 edges by Euler's formula, by Euler's formula. By Euler's formula. By Euler's formula. Rod V minus mod E plus R mod R equal to 2, equal to 2. Hence 5 mod E minus E means edges, V means vertices, plus 2 plus 2 is less than or equal to 2 of edges. 2 of edges. So that implies 5 edges minus 5 vertices plus 10 is less than or equal to 2 of E edges. That implies 3 edges, 3 of E means 5 minus 2 is 3, no? 5 edges plus 10 less than or equal to 5 vertices. LHS is 5 vertices. They transposed LHS to RHS. We obtain 5 of vertices. So that implies V equal to vertices equal to is greater than or equal to V is greater than or equal to 3 of edges plus 10 whole divided by 5. Consider equation number 1. That implies 3 of edges, 3 of vertices is less than or equal to 2 of V edges. That implies vertices. Is less than or equal to 2 by 3. 2 by 3. 2 by 3 of edges. Consider equation number 2. From 1 and 2, we obtain from equation number 1 and 2, we obtain 3 of E vertices plus 15 whole divided by 5 less than or equal to 2 by 3 E. 2 by 3 E. From 1 and 2 by 3 as it is here. This is not 15, 10. So that implies that implies 9 of edges plus 30 less than or equal to 10 of E. By cross multiplication, we are getting like that implies mod edges greater than or equal to 30. Hence proved, hence the result. Okay, next. Non-planar graphs. Non-planar graphs. This you do at home. Graph coloring. Graph coloring. Graph coloring. Graph coloring. Graph coloring. Definition. Let K be a let K be a positive integer. Let K be a positive integer. Be a positive integer. A K vertex coloring of a graph. A K vertex vertex coloring of a graph. Coloring of a graph. G is assignment of K is an assignment of K. Assignment of K. Assignment of K colors. Colors. Assignment of colors. Say 1 to K. Say 1 to K. Okay. Of each of the vertices of G. Each of the vertices of K. The vertices of K. Vertices of K. Each of the vertices of C. Just vertices of G. In such a way, no two adjacent vertices in such a way. No two of adjacent vertices have the same color. Yes. Yes. Vertices. Adjacent vertices have the same color. Have the same color. Same color. Same color. Next definition. Definition. A graph G is K colorable. A graph G. A graph G is K colorable K color. If there is a K vertex coloring, if there is K vertex coloring, K coloring, K coloring, K coloring, K vertex coloring. The minimum number of K colors, the minimum minimum number of minimum number of minimum number of minimum number of K of colors, K of colors, K of colors required to color a graph G. Required to color a graph G. Graph G. Color a graph G. Color a graph G is called the chromatic number. Is called the chromatic number. Is called the chromatic number. Called the chromatic number. Is called chromatic number. Graph G is called chromatic number. Chromatic number of G. Chromatic number G. And it is denoted by psi of G. And it is denoted by 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 psi of G. Huh? if J of Z, if Xi of G equal to K, if Xi of G equal to K, Xi of G equal to K, then G is said to be K chromatic. Then G is said to be K chromatic. K chromatic. K chromatic. K chromatic. Chromatic. K chromatic. K chromatic. So theorem. Based upon the definition, the theorem may improve. Theorem. If G is K critical, if G is K critical, K critical, K critical, then the minimum degree minimum degree minimum degree delta of G is greater than or equal to K minus 1. Proof. 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 To prove this result by contradiction. We prove this result. We prove this result by contradiction. Contradiction. Now 1 minute. So this you'll do as homework because they will cut. And so definition, edge of coloring definitions. And so page number